Hi, and welcome to Polynomials Day 2. We are going to be doing multiplication today. So I want you to show that 28 times 27 is 20 plus 8 times 20 plus 7 using an area model. What do the numbers you place inside the four rectangular regions you drew represent? Okay, so let's draw our chart. And break this down to 20 and 8 and 20 and 7. So when I multiply, I will have 400, and then 20 times 8 is 160, 20 times 7 is 140, 7 times 8 is 56. So we can say that 28 times 27 is really equal to 20 plus 8 times 20 plus 7, and then using the box method, we found that those were 400 plus 140 plus 160 plus 56, and when I add all those up together, I get 756. Then it asks me, what do the numbers you place inside the four rectangular regions you drew represent? The numbers represent the number of square units in each rectangle. All right. So use the tabular method to multiply x plus 8 times x plus 7 and then combine like terms. So it's already written out for you. Notice that on the diagonals are my like terms. So my actual polynomial answer would be x squared plus 15x plus 56. Next page. Now this is for you to try, but since that won't work for our lesson tomorrow, I'm going to use the tabular method. And I need to do a 3 by 3 chart. And I have x squared, 3x, and 1, and then x squared, negative 5x, and 2. This time I'm putting the numbers on the right side of the box because I want to find my like terms on the left side. So x squared times x squared is x to the 4th. X squared times 3x is 3x cubed, and then x squared times 1 is x squared. My next row is negative 5x times x squared, so it's negative 5x cubed. Here I will have 3x times 5x, so I will get negative 15x squared, and 1 times 5x is negative 5x. And then the last row is 2x squared, because it's 2 times x squared, 2 times 3x is 6x, and 2 times 1 is 2. So my like terms are on my diagonals. When I combine my like terms over here, I get negative 2x cubed. There's nothing to combine there, so that's x to the 4th. On this diagonal, I get a negative 12x squared. On this diagonal, I get x, and then finally I can bring down the 2. So my actual polynomial answer is x to the 4th minus 2x cubed minus 12x squared plus x plus 2. So when I multiply those two out, that's what I get. Now you don't have to use the tabular method if you don't like to. However, I would recommend trying it because it tends to make these problems a lot easier. So use the tabular method to multiply x cubed plus 3x plus 1 times x squared minus 2. So I'm going to do a 3 by 2. So I have x squared, 3x, 1, x squared, and negative 2. And when I multiply, I'll have x to the 4th. X squared times 3x is 3x cubed. 1 times x squared is x squared. Negative 2 times x squared is negative 2x squared. Negative 2 times 3x is negative 6x. Negative 2 times 1 is negative 2. Now, in this case, my diagonals don't line up for like terms, but I only have one pair of like terms, and it's just those two boxes. So my actual answer is x to the 4th, and then plus 3x cubed. I have a negative x squared and a positive x squared, so I have minus x squared, then minus 6x, and minus 2. So that is my polynomial there. All right, next page. Example 2. Multiply the polynomials x minus 1 times x to the 4th plus x to the 3rd plus x to the 2nd plus x plus 1 using the table. Generalize the pattern that emerges by writing down an identity for x times 1 times x to the n plus x to the n minus 1 plus dot 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 plus x squared plus x plus 1 for n a positive integer. So I already took care of the actual multiplication here, did all that. So I end up with, as an example, x to the 5th minus 1. So if I want to apply this, notice that we have x to the 4th and x, which gave us x to the 5th. So if I want to apply that to this problem here, I have x and x to the n. That exponent that I don't see there is x plus 1. Sorry, it's x to the 1. So I have x minus 1 times x to the n plus x to the n minus 1 plus dot 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 plus x squared plus x plus 1. I can say that, because that's the first power, when I multiply this term times this term here, I will have x to the, when I multiply, I add exponent, so it's n plus 1. And then my last term here with this last term will give me minus 1. And all my middle terms are going to cancel out because it follows the pattern in the problem. So for number 3, multiply x to the, or x minus y. Yeah, yours is a little different. I think I have you doing this one, sorry. Cross off that one, that's different. Not doing that one with you, I'm just doing this one. So multiply x squared minus y squared times x squared plus y squared using the distributive property and combine like terms, generalize the pattern that emerges to write down an identity for x to the n minus y to the n times x to the n plus y to the n. So let's make a box here and put x squared minus y squared and then x squared y squared. And when I do this, I have x to the 4th, then minus x squared y squared. Here I will have positive x squared y squared, and here I'll have negative y squared. So on my diagonal, that gives me a 0x squared y squared. This is x to the 4th, and this one is negative y, so it should be 4th, negative y to the 4th. So my answer is x to the 4th minus y to the 4th. So I'm trying to do another pattern, see what I can come up with here. So I'm going to do another box. And I have x to the n minus y to the n, x to the n, y to the n. Again, when we multiply, we add exponents. So I have x to the 2n. Here I'll have negative x to the n, y to the n. Here I'll have positive x to the n, y to the n. And then the last one, I'll have negative y to the 2n. And again, those two are going to cancel each other out. So I will have x to the 2n, and then here, negative y to the 2n. So my pattern that emerges will give me x to the 2n minus, so it should be a big minus, minus y to the 2n. So get rid of that there. So x to the 2n minus y to the 2n is the pattern that we are looking for. Okay, that was it for today's video. And tomorrow we will be working on division using the tabular method.